nonpolar surfaces. I'm going to show you some data for something like the third example. It's not hemoglobin, it's another protein, but it's the same idea. 4 subunits will come together and vary some nonpolar surfaces. This was sort of that second example. You may have some sequence of polar and nonpolar patches, and then when the protein folds into a specific three-dimensional geometry, the nonpolar parts, which are unfavorably solvated, they don't interact well with water, they become varied, in this case the green color. Now, let's look at figure 11, and I know you have some data there for you to interpret this. And I am hoping that you're at a stage where you know how to interpret negative and positive numbers. So a negative delta G is downhill. We talked about this, and that's favorable. If any, and a negative delta G is the sum of the other two terms below that, delta H plus the minus T delta S factor. So here, this is unfavorable for delta H, and usually means that heat is absorbed. And the term at the bottom, minus T delta S, that's negative, so it's favorable. And that means that the system is becoming more random. That's what the data say. And of these two terms, favorable and unfavorable, the larger one, which is dominant, is the minus 45. That's bigger than plus 35. Now remember here, this means that that's negative, then this must be positive. In order for this to happen, T is always plus. And so if minus absolute degrees Kelvin times delta S is minus 45, then delta S is plus, and that means a gain in entropy or gain in scrambledness. That's what the data say. And particularly if you look at the latter term, the entropy term, and I'm telling you the system is becoming more random, and you see 4 separate subunits coming together for this particular protein, you're telling me that's wrong. It doesn't make any sense. Because the protein is more organized. But the data say our solution is more random. And this is a major story in all of those examples I showed you. So there's something missing from our picture. Now we know this is in water, and there's certainly going to be some waters, way out here in solution, but they're really the same on both sides of this. I'm just going to sort of draw some waters out here in solution. Right? That can't be what's involved here. So what must be involved is what's different is waters that might be next door to the nonpolar surfaces. Let's try orange. I guess that works. So we may have some waters that are in contact with the nonpolar surfaces over here on the left, which then become, regular water, and they're sort of squeezed out or pushed out over on the other side on the right. And the data are then saying that this part we did not previously have in our cartoon is actually dominating the story, and the waters that are next to a exposed nonpolar surface must be more organized, and then when they go to the right, more random. Now, over there on the right, they're just plain old water out in the solvent. So this means that this special water location right here must be organized water. More organized than liquid. And the more organized form of water than liquid is our ice, or something that's more crystalline, more like we call it a lattice, L-A-T-T-I-C-E. So that means there's extra hydrogen bonds between these, more hydrogen bonds between those waters than there are in liquid water. And we need to then modify our picture. So this is a better cartoon. And you might ask, well, why would waters be more organized? And the answer, perhaps, is that these nonpolar surfaces do not interact with it. If I'm next to this blackboard, imagine I'm in waters, and back here is something that's nonpolar, this surface behind me is not making any hydrogen bonds to me. It's not interacting with my negative oxygen. It's not interacting with my positive hydrogen. And so it's sort of a quieter environment. If I have another water next to me on my right and next to me on my left, maybe we'll hold hands. Maybe we'll hydrogen bond with each other, and we don't have some distracting waters behind us trying to compete and hydrogen bond with my neighbor on my right, my neighbor on my left. I'm out here in the room, and I'm surrounded by waters all over the place. Somebody's trying to grab me here and there and behind me and all over the place, and it may be much more difficult to form a crystalline organized lattice. So that's the idea here. It's an organized solvent layer. Well, and furthermore, we then are sort of adding, in order to get it over to here, it's sort of like melting the ice. And we need to add heat to do that. That's showing up again in these data. We are absorbing heat and producing something more random. And that's because the dominant factor here is the ice-like layer of waters around those nonpolar surfaces. So this is an unusual kind of story. You don't see it in a chemistry department so much with small molecules or small surfaces. This is more you've seen in biology with membrane formation, protein aggregation, protein folding, very large molecules with lots of nonpolar portions involved in the data. And it's a little bit more science here, a little bit more complicated, and that's one of the reasons I wanted to make sure we got it done early. Now I want to skip to figure 21 and talk to you about the solubility of molecules with a titratable group and their solubilities in water. Oops. Now this first one has three different kinds of organic molecules. One of them ends in an ion, the butylamine. The other one, the butyl alcohol, ends in a polar group, but it's not an ion, hydroxyl groups. You have to go to really high pH to strip off the hydrogen. They're really not acidic. And the last one then, the pentane, is nonpolar everywhere. And they have approximately similar molecular weights, so their motions in a solvent would be similar, but they're very different in solubility. The pentane is the especially nonpolar one, only has 0.4 grams per liter. The alcohol, 91 grams per liter. And the upper one, you can dissolve as much of it as you want in a liter. All right? So the ions are especially soluble, and it's for two reasons. One is that this interacts with water. If it's a positive ion, then it will interact with the partially negative end of a water. And the other reason is when you have that in solution, if you have lots of the amines, the organic molecules will repel each other. They're not going to aggregate because you have the like charges repelling each other. So ions are more soluble. And if we then go to this figure, We have some different kinds of molecules. The more soluble form of the nitrogen-containing one is it's always the ion that's more soluble, and here it is NH plus. The left side of this acid dissociation reaction. The lower one, we have O minus as the ion, and it's the right side, the high pH form. So you have to think a little bit about this. If we have our pK and our pH, what are the two forms? Which is the ion? This is if we have a simple molecule with only one ion. And then we ask what happens. Now I'd like to ask you let's talk a little bit about aspirin and overdoses of aspirin and how we treat them, and some special coatings on aspirin these days to try so that people who are asked to take aspirin by their doctors can avoid some problems. I'd like you to think a little bit here. I'd like you to think a little bit about where is aspirin going to be more soluble. It's an organic molecule here. Acetylsalicylic acid is the organic chemical name. pK of 3. Where is it more soluble? First of all, I would like to write down the pH that goes with 0.1 molar HCl or 0.1 molar sodium hydroxide. What's the pH of a solution that's 0.1 molar HCl? Hey, somebody speak louder or raise your hand. 1. All right, thank you. And what's the pH of 0.1 molar sodium hydroxide? It's 13. Now let's just talk, because I have solutions of those here. Now what's going to be the form, the dominant form of the carboxyl group under these two conditions? What will be the form of a carboxyl group in the hydrochloric acid solution? Is it going to be COOH or COO minus? I need louder voices here. Thank you. And then on the other hand, if the pH is above the pKa, then we have the deprotonated form. So, if I dissolve an aspirin pill in hydrochloric acid and in sodium hydroxide, where do you think it would be more soluble? The base or the acid? In the base, because you have the ion form. Now, let's do this. Here's my acid, here's my base, and then you just change the camera just slightly. Now this particular aspirin has on it a type of coating. They all put aspirin as coatings. The coating on this one is to help you swallow it better, or it's as opposed to having a plastic or one of those plastic capsules. Now this is Bayer site. This is called Tolerade, and it's a cornstarch. And its purpose, a very thin coating makes it easier to swallow for people that have trouble swallowing the uncoated tablets or, the plastic-coated or polymer plastic-like capsids. So this is a coating designed just to make it a little easier to swallow. And I will come back to a different kind of coating at the end of my discussions here. So let's try this. Now it doesn't dissolve very fast. At home, what I was doing was breaking up the pills. Let's just see what we need to do here. I'm going to put one in there and one in here. I don't want to spend forever this morning. It's already taken a while. So I'm going to use some stick and break the pill a little bit and swirl it around and see what we can do. Come on. Actually, I used a different brand. This brand looks a little fussy here. This other form will be better for me. I should have, I always say don't put on a demonstration without practicing ahead of time. And I should use my other brand. This one's coatings are very, very tough here. I'm going to tell you what, I'm going to add a pillow of the other kind, where I had more success. No, can I find it? Maybe not. I'm going to be embarrassed. This is really terrible. The type I tried yesterday, it left the solutions a little bit cloudy on both sides. The particular chemicals involved were not so helpful. And maybe I'll come back